Hi everyone. In this short video we want to look at the graphs of some rational functions and try and make some sense out of the graph in terms of its equation. So let's start right here with this function f of x equals 1 over x. And one of the most important things about a rational function is that if the denominator is 0, that's going to make the function undefined. And so we'd like to understand what does that mean in terms of the graph. Well, if you plug in make a short little table of values here, and you just plug in some numbers. If you plug in x equals 1, I'd get 1, and that's this point right here. And if I was to plug in a number like, say, 4, that would give me 1 over 4. And that would be this point over here, right? It's a 1/4. And you can see as I plug in bigger and bigger numbers, if I was to plug in 100 for x, I would be just barely off the x-axis. It would be 1/100th. And you can see that as I get closer, further and further out to infinity, the graph is getting closer and closer to the x-axis. And so we call the x-axis an asymptote. Let me write that word. So an asymptote. And the same thing as I was to plug in -1, 1 over -1 would be -1, and so that's this point over here. And again, if I plug in -2, -3, -4, 1 over -4 is -1/4, you see it's also getting close to the x-axis as I get further and further out on the left of the graph. Well, what happens if I plug in things close to 0? It's interesting. I can plug in 0.0001, but I can't plug in 0. So I can plug in numbers as close to 0 as I want, and if I was to plug in, like, say, x equals 1/2, if x was 1/2, I'd have 1 over 1/2, and when I invert and multiply, that would be 2. So right here at x equals 1/2, I'm up here at 2. And you can see if I was to plug in a tenth is going to be real close to 0. So if x is a tenth, and then I take 1 over 10, that's going to be 10. And if I plugged in 1/100th, 1 over 1/100th would be 100. And so you can see the graph is going up, up, up over here. Likewise, if I was to plug in like -1/100th, you'd get -100. So basically, I have another one of these asymptotes right along x equals 0. And basically, that's what's going to happen wherever you have a rational function and the denominator is equal to 0. So wherever you have it undefined, typically that will be an asymptote, a vertical asymptote. So you'll notice over here, if we move to this one, notice that x equals -4, it would make it undefined. And you can come over here to the graph and see that right over here at x equals -4, there's going to be one of these asymptotes. Okay? And usually if we draw these by hand, we would draw a dotted line. I sometimes just use red when I use the electronic thing here. Okay? But if you wanted to, you could dot that. And that just is indicating that the graph is getting close to that but never actually touching it. And in general, whatever x value makes the denominator 0, you're going to end up with an asymptote like this, and you'll have this sort of chasm in the graph, a major, what we call a discontinuity. And you can see why that would be bad then to plug in x equals -4 or values close to -4. All right. Well, one other thing to notice here is if you plug in x equals 2, if x is 2, I would get that f of 2 is equal to 0 on the top and 6 on the bottom, which is 0. So you can see that right here at 2, there's an x-intercept. And in general, wherever the numerator is equal to 0, you're going to end up with an x-intercept. So you can see that this graph is going to come up and it's going to cross here at 2, and then it's going to go above the x-axis. All right? If I move over to this third equation, notice I can factor the numerator as the difference of squares and also the denominator as the difference of squares. And you'll notice that at x equals -3 and at x equals +3, each of those would make division by 0. And you notice that that corresponds over here on the graph to these points right here. Okay? I think I'll need to move that one over just a little bit. That one's a little bit better. Okay. So this right here, no, I can go ahead and dot those too if you want. All right. So again, that just indicates that that's the asymptote it's getting close to. And my big point is just that whatever x value makes the denominator 0 will, in general, be a vertical asymptote. Okay? And you might also notice here, actually I think yeah, that's right. Okay? And then right here, you can see that this graph crosses the x-axis, and that corresponds to x equals 2 and negative 2. So at these points, at x equals plus or minus 2, those end up being x-intercepts. Because if I plug in negative 2 or 2, I'm going to get 0 divided by whatever the denominator happens to be, and then 0 over any number other than 0 will equal 0. Okay? So, again, these guys right here, those end up being x-intercepts at x equals plus or minus 2. And then down in the denominator here, I've got a vertical asymptote at x equals plus or minus 3. Okay? All right, so in general, whatever makes the numerator 0 is going to be an x-intercept, and in general, whatever makes the denominator 0 is going to be a vertical asymptote. So we got a vertical asymptote here at x equals negative 4, and an x-intercept at x equals 2. All right? Now, I want to do one last example, and that's this one right here. Here I have a trinomial. Notice that I could factor this as x minus 2 times x plus 1 over x plus 4 times x plus 1. All right? And notice that that x plus 1 is going to cancel. It's going to cancel everywhere except at x equals negative 1. Okay? So this is going to be the same as x minus 2 over x plus 4, but x cannot equal negative 1. Okay, so I'll write that down here. So what's the graph of that going to look like? Because what you'll notice is that that looks almost exactly the same as this one right here, right? But there's definitely something different about this than there is up here. And you'll notice the graph looks almost exactly the same. So this actually is the graph of this function right here. And the only difference is, again, because for every value of x, this part's going to cancel, and it really is going to be exactly the same as we had up here. So if you just look at these graphs, they look to be exactly the same. So sure enough, it looks like right here at negative 4, there's going to be this vertical asymptote, and then also over here at x equals 2, there's going to be an x-intercept. Okay? And so it looks almost like it's the same, but notice right here, if you plug in x equals negative 1, the difference is when you plug negative 1 in here, you're gonna get, well, I'm going to get negative 1 squared is 1, and then negative when that makes 2, and 2 minus 2 is 0. The numerator is 0. And if I plug negative 1 in down here, I'm going to get, 1 minus 5 is negative 4 plus 4 is 0. So I get 0 over 0. It's the same thing as plugging negative 1 in down here, which is going to give me a 0 from here and a 0, so I get 0 over 0. And that's why right here it says nothing because it's undefined at that point. All right. Now in your graphing calculator, when you graph this, if you come over here to -1, your calculator really didn't plug in -1. It plugged in another value close to it, and so you don't really notice it unless you graph it on a special setting. But you'll notice over here, this is my setting that allows you to plug in the decimal values, and there's actually a hole right here at x equals -1. And so that's what happens if you have an x value that makes both the numerator 0 and the denominator 0 at the same time, because that's going to end up canceling everywhere except where you get the 0 over 0, and at that point you just end up with a hole in the graph, as opposed to this major chasm in the graph that you have where you don't have the x value making 0 both in the numerator and the denominator. If it's just in the denominator, then you get what we call a non-removable discontinuity. This is like the Grand Canyon, it can't be filled up. This one here we call a removable discontinuity because you could patch it. You could just plug that hole actually by just redefining the function to be this at x equals -1. Right? Notice if you plug -1 in here, you would get a -3 over a +3, which is -1, and that's exactly the y value that you would need to plug that hole. Okay, so just summarizing then, here's the fact that if you have some x value that makes the numerator 0, there's going to be an x-intercept of the graph of that rational function. And if you have some value of x that makes the denominator 0, there's going to be a vertical asymptote. And if you have a value of x that makes both the numerator and denominator 0, there's going to be a hole in your graph right there. Okay?